Hi, today's project is a 3D renderer. The renderer converts a 3D object into a 2D raster image that can be displayed with blocks. To begin, we should represent the objects we want to render using triangles. Triangles are the building blocks of 3D meshes because they can form any shape and have simple properties. Each triangle can be represented as a set of 3 vertices, each containing some freeform data such as its position, color, normal, or texture. Next, we need to position each vertex onto the raster. We will declare a function that takes a vertex as input and outputs its position. This function is called a vertex shader. The function can also output some freeform data called a fragment, which will be used to color the triangle in the next stage of the rendering pipeline. We shouldn't output a color directly at this stage because we need to interpolate data for pixels between the vertices. If we were to output a color now, it would limit us to drawing flat colors and gradients. Finally, we need a function to convert the fragment data to a color. This function is called a fragment shader. Let's start by drawing a simple triangle with a color gradient. We will declare a list of 3 vertices and group them into a triangle by reference in a second list. Each vertex contains a 2-dimensional coordinate and a color code. For the vertex shader, we will relay the position from the vertex. The raster only has 2 dimensions, but the renderer expects a 3-dimensional coordinate, so it can keep track of which triangles to draw on top. For the fragment, we will include the color code from the vertex. We should output the red, green, and blue channels separately so that we get a color gradient after interpolation. The fragment shader will simply relay the color stored in the fragment. Now that we understand the basics, let's move on to 3D. We will create a scene with a rotating cube, a movable camera, and a reflective water surface with a wave effect. The cube's mesh consists of 6 faces, each made of 2 triangles. Normally, a cube only has 8 vertices, but since they embed color data, we can only share 4 vertices per face. This gives us a total of 24 vertices. Each vertex will contain a 3-dimensional coordinate and a color. In the vertex shader, we need to transform positions in the camera's square frustum to positions on the raster. To do this, we will use linear algebra. We will represent each transformation as a matrix and apply them to our coordinates using matrix multiplication. For rotating the cube, we can simply use a rotation matrix. To move the camera, however, we need to use translation, which is a non-linear transformation. As a workaround, we will extend our coordinates to 4 dimensions and use a shear matrix. When projected back to 3D, it will appear translated. This is known as an affine transformation. From here on, we will append 1 to the end of our coordinates so they can be multiplied by 4-dimensional matrices. The camera's matrix will combine rotation and translation. It is called a lookat matrix. Finally, we will apply perspective distortion so that further objects appear smaller. This is normally done by dividing the x and y coordinates by z, the distance from the camera. Unfortunately, there are no matrices that can produce a division by z. So we will reinterpret our coordinates as homogeneous coordinates. Homogeneous coordinates represent how points are projected by treating the last component as the denominator. This means they can be multiplied by a scalar without changing their position. To visualize why this is the case, imagine you are staring at a painting. When you multiply the position of each vertex by 2, it is as if the painting has doubled in size and doubled its distance to you. These 2 effects cancel out, causing the painting to appear unchanged. This is a useful property as it allows us to multiply the coordinate by z without changing its position, thus removing the division. This lets us find our third matrix. It is called a perspective matrix and only works with homogeneous coordinates. With all three matrices, we can write our vertex shader. Since we are working with solid colors, we can output the color to the fragment shader as a single numeric value. Using the same principles, we can render a plane for the water. To generate the reflection texture, we can render the cube to an off-screen camera positioned at water level. We will replace the color code in the mesh with image coordinates. This will give us a gradient between 0 and 1 after interpolation, which we can use to sample the image inside the fragment shader. To add a blue tint, we can use this function. We can distort the image coordinates using a sine wave before sampling to create the wave effect. To make it oscillate over time, we can multiply the wave by the sine of the current timestamp. So far, I've explained how to tell the renderer what to draw. Let's take a look at how the renderer converts this data to a raster. Every time the renderer is invoked, it passes each vertex in the mesh through the vertex shader. This gives us a list of positions and fragments. The renderer then draws each triangle in the mesh. To draw a triangle, it iterates through each pixel in the raster and finds its barycentric coordinate. Barycentric coordinates describe positions based on their relative position to each vertex of a triangle. For example, the coordinate at the center is 1/3, 1/3, and 1/3. The coordinate at A is 1, 0, and 0, and its opposite midpoint is 0, 0.5, and 0.5. We can find the barycentric coordinate using this function. Using the barycentric coordinate, we can easily determine if a point falls inside the triangle. Pixels that are outside can be ignored. Next, we will find the depth of the pixel. If it is greater than the existing depth, then the pixel is occluded by another triangle and can be ignored. Finally, we can use the barycentric coordinate to find a weighted average of the three fragments and pass it to the fragment shader for a color. We should also store the depth so it will occlude other triangles that are drawn later. That is all for today. Thank you for watching, and I hope to see you next time.